Hello, my name is Paulo Pereira and I would like to present you this new procedure to optimize the intercarrier spacing in superchannels when they have to cross several optical nodes which have inside WSS filters. This procedure also optimizes the bandwidth of the WSS filters. It is well known that ever-increasing need for capacity in long-haul transport networks is related with the expansion of the Internet traffic worldwide. So it is vital to find the most cost-effective solution to cope with the present and perceived future demand. The idea behind the usage of an elastic optical network is the use of superchannels, bandwidth variable wavelength selective switches inside the reconfigurable optical add-drop multiplexers, and use of improved routing and spectrum assignment algorithms. The superchannels can have different capacities and different bandwidth within a flexible grid optical network, since the bandwidth of a superchannel can be changed by changing the number of subchannels and the intercarrier spacing. The WSS bandwidth must be able to change accordingly. In this work, we studied the superchannel transmission through a cascade of WSS. The intercarrier spacing can increase the crosstalk between subchannels, and the WSS filtering can increase the signal distortion. So, we have to optimize the WSS bandwidth and the intercarrier spacing. To model the WSS, we can use two models, the super Gaussian model and the analytical model. In this work, we used the analytical model. We simulated superchannels with 2 up to 10 subchannels. We choose that all subchannels have an OSNR penalty below a specified threshold after a certain number of WSS. This way, the center subchannel and the edge subchannels have the same performance. We choose 1.5 dB for the threshold and we choose 20 WSS filters. We simulated superchannels in different scenarios, different modulation formats, symbol rates, roll-off factors, number of WSS, WSS bandwidth, number of subchannels, and different intercarrier spacings. In this work, we used Monte Carlo simulations. We used different target bit error rates depending on the symbol rate, and for the signal power level at the transmitter per subchannel, we used 0 dBm. This is the schematic model of the optical path we simulated. There you can see the cascade of WSS filters that are inside the optical nodes. The optical signal has to cross all these filters in its path from the transmitter to the receiver. This way, we can simulate the bandwidth narrowing effect that results from the cascaded WSS. In the figure, it is also shown that we perform noise loading in the simulations. To simulate the transfer function of the WSS, we could use the super Gaussian function. But if you do this, we have to know the order of the super Gaussian. Notice that the WSS bandwidth for the superchannels can have more than 300 GHz. The order to use for a bandwidth of 300 GHz is not equal to the order used for a bandwidth of just 37.5 GHz. So the question is, which is the order that should we choose? Well, it's better to use another model. We choose to use the analytical model. This model works equally well with bandwidth of 37.5 GHz or 300 GHz. The only thing we have to choose is if you want a sharp filter or a smooth filter. For this, we only have to select the value of the BOTF parameter. For a sharp filter, we can choose, for instance, 8 GHz. For a smooth filter, we can choose, for instance, 16 GHz. The B parameter is the minus 6 dB bandwidth of the WSS filter. In this figure, we can see the impact of the BOTF parameter on the sharpness of the filter. For this work, we use the BOTF of 8.5 GHz. In this work, all WSS bandwidth are at minus 6 dB because this is what is used by the analytical model. From the figure, it is clear the choice for this bandwidth. We used several modulation formats. We used the gray mapping whenever possible, of course. But for the 8 QAM modulation format, that is not possible. So we use the mapping that allows the lowest number of wrong bits in a wrong symbol detection to reduce, obviously, the probability of bit errors. The figure illustrates the modulation formats used after 20 cascaded WSS for a symbol rate of 28 gigabaud. In the figure, we can see the spectrum of a superchannel with 10 subchannels. The symbol rate is 28 gigabaud and the roll-off factor is 0.1. The intercarrier spacing is 28.9 GHz. In the top figure, we see in red the spectrum of the superchannel after the first WSS filter. The blue line represents the transfer function of the first WSS filter. In the bottom figure, we see the spectrum of the superchannel after 20 cascaded WSS filters, and the blue line represents the transfer function of these 20 cascaded WSS filters. We can clearly see that the blue line now presents a lower bandwidth. The cascaded WSS create this bandwidth narrowing effect. Now we select the right edge subchannel, and for 3 modulation formats, we see how the intercarrier spacing influences the OSNR penalty. With the lower intercarrier spacing, the penalty is related with crosstalk, and for a higher intercarrier spacing, the penalty is related with the WSS filtering. Another important aspect is the dependence on the number of WSS. This means that optimum intercarrier spacing depends on the modulation format and on the number of WSS. Of course, these results depend on the WSS bandwidth selected. We choose bandwidth so that penalties are below 1.5 dB in all subchannels. We can see that higher modulation format orders are less tolerant than lower modulation format orders. This is for the right edge subchannels of the superchannel. Now we select the center subchannel, and again, for stream modulation formats, we see how the intercarrier spacing influences the OSNR penalty. The penalty increases when we lower the intercarrier spacing, because it is related with crosstalk. We can see that it does not depend on the number of WSS. The WSS bandwidth is selected so that penalties are below 1.5 dB, and WSS bandwidth is, of course, the same as for the edge subchannel. Since we want to choose an intercarrier spacing and a WSS bandwidth that allows the same performance for all subchannels, we need to combine the results from the edge subchannel and from the center subchannel. These are the combined results. For each intercarrier spacing, we added the OSNR penalties from the edge subchannel and from the center subchannel. From these figures, we can choose the optimum intercarrier spacing, depending on the modulation format and on the number of WSS in the optical path. With this procedure, we achieve the lowest penalty for all subchannels and always below 1.5 dB after 20 WSS and using the lowest WSS bandwidth. This way, we achieve the highest spectral efficiency for the superchannel. This table shows the results for a symbol rate of 28 gigabaud for QAM and 16 QAM modulation formats for a superchannel with 2 up to 10 subchannels. We see the columns with the number of subchannels, the WSS bandwidth, the intercarrier spacing, and the OSNR penalties in a center subchannel and in an edge subchannel. These are the optimum values for the bandwidth and intercarrier spacing. We can see that for the same number of subchannels, the modulation format order sometimes increases the bandwidth. This increase is 12.5 GHz, which is the frequency slot with granularity of a flexible grid optical network. We can see that intercarrier spacing is usually slightly larger than the Nyquist bandwidth, and it increases as we increase the modulation format order of the signal. This other table shows the results for a symbol rate of 32.5 gigabaud. We have the same columns as in the previous table. With this increase in the symbol rate, the bandwidth increases for the superchannels. For those with 8, 9, and 10 subchannels, the increase is by 3 frequency slots. As in the previous table, for the same number of subchannels, the modulation format order sometimes increases the bandwidth by 1 frequency slot. If we increase the modulation format order, we observe sometimes an increase in the bandwidth by 1 frequency slot. As in the previous table, the intercarrier spacing is usually slightly larger than the Nyquist bandwidth, and it increases as we increase the modulation format order of the signal. Now, it's interesting to see how this optimization translates into the spectral efficiency of the superchannel. This figure provides us that information for a symbol rate of 28 gigabaud. The blue line shows the WSS bandwidth increase as we increase the number of subchannels from 1 up to 10. For the 4 QAM modulation format, this means a variation from 100 gigabits per second to 1 terabit per second. The red line shows that with 3 or more subchannels, the spectral efficiency is between 3 and 3.5 bits per second per hertz. In this other figure, we see the results for a symbol rate of 32.5 gigabaud. We can see that the blue line is now showing higher values. The red line shows that with 4 or more subchannels, the spectral efficiency is around 3 bits per second per hertz. The trade-off is between the spectral efficiency and the reach of the optical signal. In this study, we selected WSS bandwidth so that all subchannels have the lowest OSNR penalty below 1.5 dB after a cascade of 20 WSS. Another possibility would be to choose WSS bandwidth that are integer multiples of 37.5 GHz or 50 GHz. However, nowadays, the network operators try to avoid a dynamic number of subchannels. We saw how the procedure presented in this work allows to achieve an higher spectral efficiency. In this presentation, we showed this new procedure to obtain the optimized WSS bandwidth and intercarrier spacing. We used superchannels with 2 up to 10 subchannels. All the subchannels have an OSNR penalty below a specified threshold and after a certain number of WSS. From the tables, we can see that optimum intercarrier spacing is at most 1.1 GHz, larger than the Nyquist bandwidth, but it can be much lower, depending on the symbol rate, modulation format, number of subchannels, number of cascaded WSS, and roll-off factors. All of these must be considered to obtain the optimized WSS bandwidth and intercarrier spacing to achieve the highest spectral efficiency in the superchannel. It must be emphasized that the number of WSS has a very significant impact on the optimized WSS bandwidth and intercarrier spacing. This concludes the presentation. Thank you for your attention. Feel free to contact us. Bye.